Hello and welcome, students. Welcome to Lazy Chemistry, and today we're going to go ahead and talk about the hybridization of orbitals, which is an atom's or an element's way to try and make sure that its electrons are in the lowest possible state by combining two electrical orbitals when it bonds. Okay. So sometimes when we bond, what will happen is that we'll kind of mash together some orbitals in the hopes that we'll go ahead and make an orbital that's going to be slightly lower in energy than it would be if we did not hybridize it here. Okay. And I'm going to try and keep it relatively basic for you. There is some controversies that go along with this, but we won't go too far into them and we'll kind of just ignore them. Okay, so what we have here is we have an atom, and we're essentially going to use this section to get into how we determine some of these structures and start to talk about some of the molecular geometry that we're going to go in here. Okay. Right, so first, what is hybridization? Hybridization is kind of the phenomenon of intermixing orbitals of different energies, so as to kind of spread out their energies a little bit and put them in a new orbital that has generally a little bit less energy than their first starting orbital, or at least for some of the electrons, their first starting orbital. Okay. And just a reminder that we have our four orbitals. We have the S, P, D, and F. And in general, we're going to be only concerning ourselves in this course with S and P. There's some controversy right now whether S and D hybridize at all. But since there's controversy, we're not going to go into that one. It was established that they did, but there's starting to get a lot more doubts as to whether there is any hybridization going on there. Okay. Remember, an S is a spherical. P's are dumbbell shaped. D and F are more complex, but that's just how it is. And these are the orbitals that we're going to be concerned with. And we're only going to be concerned with these first three. We're going to be talking about the S and P orbital, which is one S and one P. Then the second one is an Sp2 orbital, which is one S and two P's. And then the third orbital that we're going to concern ourselves with is Sp3, which is one S and three P's. And how we're actually even going to determine this is we're going to determine this based off of how many bonding groups there are in that compound, or how many electron groups that we have. Okay? And in general, if we only have two electron groups, that's going to be an Sp orbital. Okay? So it's going to be one S and one P, because we only have two electron groups that we're worried with, so we only need two orbitals. If we have three electron groups, well, we need three orbitals, so we need one S and two P's. If we have four electron groups, then we're going to need to have four orbitals, which is going to be one S and three P's. And that's kind of like the easiest way that you can go ahead and think about it here. That the more electron groups that you have, the greater amount of hybridization, or the greater level of hybridization that you're going to have here. So let's go ahead and go in. And, that entire slide was kind of useless. Okay, and this is just showing electrons. We're going to skip it, and this shows video, blah, 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 blah. All right, so first one, Sp orbital, okay, where we're going to go ahead and take one S and a P, and we're going to go ahead and make an Sp orbital. Boring. Okay, now, in general, and we'll go ahead and get this one shape thing in here. And we're going to go into this in a lot more detail in a bit. But when we get one S and one P orbital, we'll form two Sp hybrid orbitals. Okay? In general, when we get those, we're going to go ahead and get a linear arrangement of our atoms, and the bond angle will be 180 degrees. All right. So a perfect example here is acetylene. Okay, it's C2H2. As each carbon atom in this molecule has 2 points of attachment, each carbon in acetylene is Sp hybridized. Okay, so we'll go ahead and draw it out here. Let's get rid of this one. This is the second time I've had to do this one here. Okay, so acetylene is C2H2. Okay, we're going to go ahead and look at our carbon, make sure that our bonding is good, and our carbon is not bonded well right now. Okay, so we have to add more bonds in there. Okay, now this carbon has 2 electron groups. Okay, we have electrons here, we have electrons here. Therefore, this is called Sp hybridized because we needed one S and one P to come together to make this new hybrid orbital. All right. And this one also ends up being Sp hybridized. Okay. So let's go ahead and talk a little bit about what is going on here with this particular carbon molecule. All right, let's pull this one over here. All right, so these carbons are coming together, and normally carbon ends with 2s, and it has 2 electrons in there, and then we have 2p, and we have 1 electron here, 1 electron here. Okay. And we have both of these carbons coming together. All right. When these carbons come together, and they're coming together with the hydrogen or with the other one, what they're going to do is they're going to go ahead and say, okay, you know what? When we bond here, we don't want to go ahead and put more electrons in here because it's just going to be a higher energy electron. Let's go ahead and take one of our bonds from here and this orbital here, and we're going to go ahead and make an Sp hybridized orbital. Okay, and this Sp hybridized orbital is going to go ahead and be right here. Okay, and that Sp hybridized orbital is going to end up making it so that when they do take those extra electrons in there, the electrons are going to be at a slightly lower energy level than normal. Okay, and so when this carbon bonds, what it does is it puts those in that energy level so that it has just a little bit more wiggle room in terms of, you know, making sure that the electrons are at their lowest possible energy level. All right. So when it combines, those electrons end up coming at a little bit lower energy level. And if you think back to the lesson that we had before, where we were talking about how when bonds come together, they come together with they release energy. Well, this is one of those examples that when this bond and this new orbital forms, the electrons are at a little bit of a lower energy level than they were before. And therefore, you know, it's going to be able to release some of that energy that's right there. All right. So at this point right here, you know, this would be what it would end up looking like. And this is kind of like our first bond here and our first bond here. What we'll end up learning here is that the second bond that we have here, which are these bonds and these bonds, these are what are called pi bonds. And these are actually both these last 2 p orbitals of carbons are bonding right on top of each other. And we'll show another picture of that in just a little second. But it's really interesting that they make these hybridized orbitals and then they have these p areas that they can go ahead and also bond with to make triple and double bonds like this. Okay, and what thing do I have to go to here? This one? Yeah, okay. Alright. So this is what it formally looks like, but they don't have this one in the energy thing, so I kind of dislike it here. And also they put it as Sp2 here. I don't like how they did that. Okay. So this is really just, the 1s orbitals. We make 2 Sp hybridized orbitals, and then we still have those 2 unused orbitals. And this is what the new Sp hybridized orbital is going to be. And notice that it's 180 degrees where the electron groups are. Okay. Now those electron groups repel each other, so them being 180 degrees is exactly what they want. Okay. And yeah. Alright. And now this here, the Sp, as I said before, that's going to be our sigma bond, and we'll get into this a little bit later. Our sigma bond is our first bond, okay? So get used to that idea that any first bond is going to be a sigma bond. And then the bonding between the p orbitals, those are our second and third bonds. Those are called our pi bonds, okay? So the other orbitals are also bonding here. So we're going to have, essentially one bond between the z orbitals, okay? That's one pi bond. That's our double bond. And then we also have our bond between the y orbitals, the py orbitals, or the orbital that's in the y direction. And that's our second pi bond there. Okay. Next is going to be Sp2 hybridized. Okay. And this is a case where we're going to have 1s and 2 p orbitals. Okay. So that means that we should expect to see 3 bonding groups. Okay. So that's our expectation. We're expecting that in a second here, we're going to have 3 electron groups that we're going to be worried about. Okay. So here we have ethene. Okay. Ethene is going to be C2H4. So let's go ahead and draw that out. Let's go here. So C, so connect up our C's first. And we have 4 hydrogens. And notice here that this carbon has 1, 2, 3 electron groups. Okay, we said before this is going to be Sp2 hybridized, which means 1s and 2 p's. That's 3 orbitals. Here we have 1, 2, 3 orbital groups. That's exactly what we were expecting. Okay. Okay, and this will just go further into it here where it's showing like, hey, we have 1s orbital combining with 2 p orbitals. Okay, and these are 120 degrees away from each other, which makes sense. 360 divided by 3 is 120. Okay, and this one, it's also showing that we have a pi bond. So let's go back to our image here before. We have our single bond, and then we have 1 double bond, which is kind of, what we expected there. Okay. Next is Sp3. All right. This one's going to have 1s and 3 p's in the hybridization. Okay. And, oh, man, why would you do, like, methane? Okay. Never mind. They say to use methane here. Let's disagree. We've been using 2 carbons this whole time. Let's go ahead and continue on. All right. So, we're going to use ethane. Okay. Now, we said that this one is Sp3, which means that we should expect 4 electron groups that we need. Okay, so sp3. 1, 2, 3, 4. Okay, so 1, 2, 3, 4. We have 4 orbitals involved. That's what's going on here with sp3. Okay. This one, we have 109.5. If you entered it into your calculator and you took 360 divided by 4, you should end up getting 109.5. Let's do a quick look. Okay. Oh, I guess it says 90 degrees. Man, that looks embarrassing to me. Why is it? No, 90 degrees all over. Let's try this. Bond, angle, methane. Oh, that's right, because we have one. Never mind. Never mind. Even your teacher can derp here, because we're not going in a circle, we're going in 3 dimensions. Okay? So, in 3 dimensions, we end up making a tetrahedral type molecule. Where we're going to end up looking something that's similar to this. So, okay, so we're going to end up making a molecule that's very similar to this, and these angles end up being 109.5 degrees. Man, you could tell that I'm recording this on a Sunday when, I definitely am trying to avoid 90 Day Fiancé. Alright, so next, we're going to take a look here. Notice that this is the new hybridized state for it, where we have our 1s orbital, and instead these orbitals have all turned into sp3. And that's what that one looks like. Now, this one, the 3sp3, whatever. This one, and this one, we're not really all too concerned with because there are much other likely scenarios going on. Okay. Next, we're going to briefly talk about sigma bonds. Okay. Sigma bonds are the first bond that we get. So, when we go through this section, one thing that we're going to do is we're going to go ahead and talk about sigma bonds and pi bonds. And sigma bonds are going to be usually our sp hybridized orbital first. Okay, so when we talk about sigma bonds, we're always going to be talking about the first bond that we get in an atom. Okay, and so one thing that will often happen is that you will be asked and tasked with determining how many sigma bonds and pi bonds there are. Okay, and our sigma bonds are always going to be the first bond that we have. Okay, and they are often the strongest bond in that molecule. The pi bonds are going to be the extra bonds that we have. Okay, so here in this case, this molecule right here, has 1, 2, 3 sigma bonds. Okay, these two right here, the double and the triple bond, are both our pi bonds. Okay, our sigma bond is going to be our sp hybridized bond, and then our pi bonds are just what's made with the leftover p orbitals that we had from before. Okay. In this molecule here, we took 2 p orbitals and we left 1. So we would expect that we would have Sp, and we have 1, 2, 3. And then we had 1 p left over. Okay. So that means that we have 1, 2, 3 Sp for this carbon, and then 1 leftover p orbital. Okay. So that means that we have 1, 2, 3 sigma bonds on this carbon, and 1 pi bond. All right. And that's what we're talking about here with this one here. Okay. So with this section, I think that in addition to this lecture section, the reading section is also going to be pretty important for you guys. I'm going to go ahead and recommend that you go ahead and read the section on this to go ahead and get another good grasp, and we'll have a little bit of practice with this as well. In general, the things that you're going to be most often tasked with is writing down what type of hybridization it is, and then also telling how many sigma bonds and how many pi bonds there are. Okay. For right now, that's going to go ahead and close us down for hybridization. Okay. I hope this all meets you well and you have great understanding. And as always, remember, be lazy.